Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 153, titled Find Minimum in Rotated Sorted Array. So suppose an array of length n, sorted in ascending order, is rotated between 1 and n times. For example, the array nums equals 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2 if it was rotated 4 times. So nums at 0 would originally be set to 0, and the new nums at 0 would be set to 4, right? Because we're rotating it 4 times. So if we rotate the same array 7 times, we can actually observe that we'd get the same exact array. And that actually leads to the observation that if we actually rotate an array of length n times, where n is equal to the length of the numbers, then we'd get the same exact array, right? In this case, the length of this array is 7, and so since we rotated 7 times in this case, we would actually get the same exact array, with the arrangement of all the elements staying the same as our original input sorted array. So it also says that notice that rotating an array from a at 0, a at 1, a at 2, up until a at n minus 1, one time results in the array switching or rotating to a at n minus 1, a at 0, all the way up till a at n minus 2. And that's also a very good pattern to recognize to actually efficiently and optimally solve this problem. So we're given the sorted array nums of unique elements, and we have to return the minimum element of this array. And something really important, again, is that we are actually given a rotated array of unique elements, right? This is a valid set, and that actually rids of any weird base cases that we'd have to address in our code otherwise. So we have to return the minimum element of this array, and we have to write an algorithm that runs in big O of log n time. And honestly, when you see big O of log and runtime complexity time in really competitive programming or Leetcode in general, always just immediately think of binary search, because 80% of the time, even 90% honestly, binary search would be the correct way to go when it says that you have to actually implement a function or algorithm that runs in big O of log n time. So honestly, this is a kind of a weird problem, because if you actually scroll down and check the constraints, it says that when n is equal to the nums.length, or the length of the nums, n is not going to exceed the value of 5,000. So this actually indicates that we can have operations up until and even exceeding big O of n, which in this case, if we were to have a program that actually runs in big O of n, we would see that if I just return the minimum of the nums input array, if I were to submit this, this would actually work, right? And that's because this is a big O of n algorithm, and in the description down below it says that n is not going to exceed 5,000, where n is the length of the numbers. And so big O of n would only result in 5,000 operations, which is less than the standard exceeding amount of 10 to the power of 8. And so this would actually be a valid operation, or a valid runtime complexity. But of course, we can do a lot better, and that's the reason why we only beat 6.6% of users and take 51 milliseconds to actually run. And the way we actually do better is actually, of course, implementing the binary search. But before we actually get into that binary search algorithm, let's just go ahead and look at the examples. So in example 1, we have a nums to be an input array of 3, 4, 5, 1, 2. Note that our pivot point essentially is going to be at 5, where basically instead of our minimum array or nums at 0 being 1, it's changed or rotated 3 times for it to be at 3 for nums at 0. And we'd output 1 because 1 away from our pivot point, or 1 index above our pivot point at 5, we see that 1 is right next to it. And so the original array was rotated 3 times, and so our original array was 1, 2, 3, 4, 5. So applying that same logic to examples 2 and 3, we would output 0 and 11 respectively using that same logic. So although you guys do know what algorithm to use, in this case it's going to be binary search, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you guys how I would optimally solve this problem. Okay, so to solve this problem optimally and efficiently, we're actually, of course, going to take the binary search algorithm approach, but we're actually going to be using a modified binary search algorithm. It isn't going to be the standard find nums at mid until it actually equals the target style by the binary search algorithm. It's going to be a little bit different, and I will explain how that actually works. So like usual for the binary search algorithm, I'm going to set L and R to be equal to 0 and the length of the numbers minus 1. So just the very last index of the nums input array for R, or the right variable, and the left variable initialized to the very leftmost index. In this case, is going to be 0. So once we actually set those variables equal, or our 2 pointers for this algorithm, let's basically have our while loop like we always do in the binary search to actually check while L is in bounds of R. But in this case, instead of doing while L is less than or equal to R, we'll simply do while L is strictly less than R. And the reason why we do that is the condition L is less than R ensures that the loop continues as long as there is more than one element to consider. If we used while L is less than or equal to R, the loop would potentially overextend and might not terminate at the correct point. And since we're always adjusting either L or R in a way that brings them closer together in the binary search algorithm, using L less than R ensures that the loop stops when we have narrowed the search space down to one element, which is going to be eventually our minimum. And you guys will see how that goes a little bit more in the code, right? So while L is strictly less than R, basically in bounds of our right pointer or variable, we're going to set our middle index to be, of course, the sum of the two variables, whatever values they are in this specific level or iteration of the while loop, and of course integer division by 2 to get that actual true absolute middle value or middle index. And then we actually basically have to have a series of conditionals to check if we have found our minimum value or not. So first, for the very first conditional, we're going to say if nums at mid, again note that this is a modified binary search, so if nums at that middle index, if it's actually greater than nums at that index R, then that means we have to shift our left pointer equal to the middle index plus 1. And to better visualize of how that actually works, and let's just take example 1 for example, alright? Nums at mid would be equal to 5, right? And in this case, nums at R would be the very last index, or basically 2. We know that nums at mid is greater than nums at R because, of course, 5 is greater than 2. And since that's the case, we want to actually get our left pointer and put it equal to mid plus 1 because we have to explore the right side of the array because we know that our minimum variable or our minimum value in the original array would be in the leftmost side of the array because we haven't actually found our maximum yet. And so that's basically how that would work. Now, if nums at mid is actually not strictly greater than nums at R, we can simply have one more else conditional, and that says nums at mid is less than nums at R, and we can actually decrement our right or R pointer to be equal to mid, okay? And for example, let's just take example 3, for example. In this case, our nums at mid would be 13, and our nums at R would be 17. Note that 13 is less than nums at R, which is 17, and so we know that the minimum value is going to be in the left portion of the array, and so we get R and set it equal to 13, right? So now our R would be 13, and we keep exploring the left part of the array until we actually find our minimum value, which in this case is going to be outputted to 11, right? So once we set R equal to mid, we can actually exit this while loop and eventually return nums at that index R. And unless I made any syntax errors here or spelled something wrong, this should be completely fine. This should be accepted. And as you can see, it's just about as efficient as you can get, beating 90.81% of users runtime complexity-wise, and memory complexity-wise beating 46.93% of users, right? So you may kind of be confused, why do we actually return nums at R, right? Why don't we just return R, or why don't we just return nums at L? And the reason why we do that is, at the end of the loop, both L and R will point to the same index, which holds the minimum element. And since R is the variable we're adjusting to converge toward that minimum value, returning nums at R gives the correct result. So returning nums at R works because the binary search algorithm, it basically narrows down the range until R or L, since they converge, points to the smallest element. And at that point, nums at R would contain that minimum value, okay? So runtime complexity-wise, this is going to be big O of log n, where n is the number of elements in the array, or the lengths of the input array nums input. And the reason why that is because this is the binary search algorithm, or which is the standard algorithm for O of log n operations, and that's why this is going to be big O of log n. And to better explain why binary search is actually big O of log n, it's actually because we are effectively halving the search space in every iteration of the binary search loop by moving either L or R closer to that minimum element, right? And space complexity-wise, this is obviously going to be big O of 1, or basically constant type, because the algorithm uses a constant amount of extra space, only needing a few variables R, L, and mid for the binary search algorithm, and we're not actually using any extra data structures to store any elements or inputs from our input array nums, and so this would be a constant time solution. So if you guys enjoyed this solution and learned something new, please consider liking this channel and subscribing to my channel. It really does mean a lot. And without further ado, I will see you guys in the next video. Bye-bye.